Imagine managing a $5 billion pension fund.
That is a massive amount of stress to carry around.
Right. I mean, you are entirely responsible for the retirements of tens of thousands of teachers, firefighters, and nurses.
Real people, relying entirely on your models to survive their retirement.
Exactly. And the market is just ticking away on your terminal. And then suddenly, a central bank across the globe announces this microscopic shift in interest rates.
We are talking maybe 0.01%.
Yeah, a fraction of a fraction. To the average person on the street, that is absolutely nothing. It is a rounding error.
They wouldn't even notice it.
But to you, running that specific fund, that microscopic shift sends this massive immediate shockwave through your portfolio.
Oh, absolutely. It threatens to wipe out hundreds of millions of dollars.
Right, and like 10 years of compounding returns just gone. So the question is, how do you protect that money before the shockwave even hits?
Well, the answer to that question about the actual shield that protects the modern financial world, it actually lies in an intellectual feud from the 1600s.
Which is just wild to think about.
It really is. It's the ultimate butterfly effect, mathematically formalized. And, you are right to start there because that is the reality for our listener today.
Yeah, if you are an actuarial student tuning into this deep dive, you're literally training to be the architect of those financial shields.
You aren't just crunching numbers in a vacuum. You are learning to quantify the exact instantaneous impact of those shockwaves.
Okay, let's unpack this. We have been on this journey together through the architectural blueprints of mathematics. We looked at sets as the raw materials, right? And then functions as the engines that drive the mathematical universe.
But an engine just sitting on a test block isn't doing any real work.
Exactly. Today, we are putting that engine on the highway. We are demystifying differentiation.
And we are doing it specifically for you, the actuary.
Right, because you already know how to calculate a basic derivative on paper. I mean, you've done the power rule, the chain rule.
The quotient rule, yeah.
You've done them 1,000 times in your early calculus classes. But what we really need to unpack today is how that mathematical abstraction maps directly onto the actual survival models and pricing algorithms you are being tested on right now.
That is the critical bridge to cross here. Because the mechanics of differentiation, they are just syntax.
What do you mean by that?
Well, the actual grammar, the philosophy of what you are doing is shifting your perspective from a world standing completely still to a world in perpetual, often violent motion.
Ah, okay. So you are moving from the arithmetic of states to the calculus of sensitivity.
Exact.
Which is a massive paradigm shift. And I think to understand the weight of it, we do need to glance back at the history, just briefly.
It sets the stage for why this is so difficult to conceptualize in the first place.
Right, because before the late 1600s, humanity essentially had a high-definition camera, but it could only take still photos.
It was completely blind to the video of reality.
Yeah, that is a great way to put it. The mathematics of the era, algebra and geometry, they were beautifully rigorous, but utterly static.
You could perfectly calculate the area of a triangular field, right?
All right.
Or you could perfectly balance a merchant's ledger at the end of the day, but the universe just refuses to hold still for our snapshots.
It really does.
I mean, planets orbit in sweeping, continuous ellipses. Apples accelerate as they fall from branches.
Wealth compounds dynamically over time.
Exactly. And the greatest thinkers of the day, they were hitting a brick wall.
Because they could not mathematically describe the fluid reality of movement.
This raises an important question. How do you mathematically capture something that absolutely refuses to stop moving?
Right. It's the difference between knowing where a planet was yesterday and where it is today versus understanding the exact mechanics of how it is moving right this very second.
And that specific frustration birthed one of the most intense dramas in the history of science.
Oh, the Newton and Leibniz feud.
Yes, between Isaac Newton in England and Gottfried Wilhelm Leibniz in Germany.
Two absolute giants of history. And they independently shattered that brick wall, right?
They did. Newton approached it from the perspective of physics.
Right, the whole apple falling thing.
Yeah, he was fleeing the plague, sitting on his family farm, watching objects flow through space. He invented what he called the method of fluxions to calculate the exact speed of an object at a frozen single instant in time.
Wow. And then Leibniz.
Leibniz approached it from geometry. He was looking at curved lines, trying to figure out how to calculate the perfect, precise slope of a curve at one single microscopic point.
And Leibniz actually published his findings first, right?
He did, which sparked a bitter, ugly war. Newton's followers accused Leibniz of theft. Leibniz relentlessly defended his independent genius.
It literally split the European scientific community for
It
decades.
really did. But history vindicated both men as independent discoverers of the exact same truth.
Here's where it gets really interesting, though. One man looked at the physical reality of gravity flowing space,
Right.
and another looked at the pure abstraction of curves in geometry. Yet both uncovered the exact same underlying grammar of reality.
Calculus. Specifically, the mathematics of continuous change, with differentiation as its first massive pillar.
It proves that differentiation isn't just some arbitrary human invention.
No, it is a fundamental property of the universe.
Yeah. Whether you are tracking the acceleration of a falling apple, or to bring it into the modern era, for our listeners, modeling the continuous compounding of an interest rate.
The exact rate of change governs it all.
Okay, let's ground that in something really visceral for a moment before we dive into the actuarial models.
What's that?
Let's talk about the standard road trip analogy from our sources. Say you're driving from Cape Town to Johannesburg.
A classic route.
You've got the distance, you've got the time. Calculating your average speed is just elementary algebra, right?
Total distance divided by total time. Say it's 100 kilometers per hour.
But for an actuary, that average is completely useless, isn't it?
It is dangerously misleading.
Why dangerous?
Because an average masks all the volatility. If you are calculating the average speed over a 10-hour trip, you are entirely blind to the fact that at a specific frozen millisecond on the highway, you are accelerating to 140 to overtake a massive semi-truck.
Or slamming on the brakes because you hit a pothole.
Exactly. Average speed fails you there.
So differentiation is, quite literally, the act of looking down at the speedometer at that exact frozen fraction of a second.
Yes. You shrink the window of time into an infinitely small slice until time practically stops.
And you extract the precise, instantaneous rate of change.
You aren't asking what happened over the last hour. You are asking what is happening right now at this exact infinitesimally small moment.
I love the topographical analogy for this, too. If a function is a massive hill you're hiking up, the derivative isn't the total elevation gain of your hike.
No, it's the exact steepness of the slope directly beneath your boots on one specific step.
What's fascinating here is how this mathematical tool allows us to basically conquer the infinitesimally small.
And that concept, instantaneous sensitivity, is the absolute core ethos of the actuarial profession.
Right. It is not enough to just know the state of a financial ledger today.
No, the entire job revolves around measuring exactly how fast the variables in that ledger are moving right now.
And how violently your models will react if reality takes a sudden turn.
Precisely.
So what does this all mean for you, the actuarial student taking these brutal exams?
It means differentiation is your primary weapon for predicting the future.
It's how you measure the shock waves before they hit.
Yes.
So let's prove this. Let's walk you through the specific pillars of your coursework. We aren't going to talk about abstract cars anymore.
We are going to talk about human life.
Yes. The first major application. Survival models.
This is the bedrock of life insurance and pensions.
Now, in your early statistics courses, you dealt with discrete probabilities, right?
Yeah, you looked at the probability that a person aged 45 dies before their 46th birthday.
In actuarial notation, that's Q sub X.
Exactly. That is an annual probability. It is a broad average over an entire year.
Right, it's the Cape Town to Johannesburg average speed. It treats the entire year as one big, clunky bucket.
But human aging does not happen in clunky annual buckets.
No, obviously, yeah.
Aging is a continuous, relentless physical process. Every second, every millisecond, the cells in a human body are degrading.
So the risk of mortality is constantly flowing.
Yes. And to price complex, multi-decade life insurance products accurately, actuaries cannot rely on discrete annual steps. They need a continuous model,
Which introduces the concept of the force of mortality.
often denoted as mu sub x.
I want to really dig into this, because this is where the textbook math meets the actual biological reality. What exactly is the force of mortality, mathematically speaking?
Mathematically, if you have a survival function, let's call it S of x, which represents the probability of a newborn surviving to exactly age x, the force of mortality is the negative of the derivative of the natural log of that survival function.
Okay, let's strip away the notation for a second and talk about what that actually means conceptually. Why use the derivative?
Because the derivative gives us the instantaneous rate of failure.
Okay.
Imagine the survival function is a curve gently sloping downwards as age increases because, fewer and fewer people survive to older ages.
Right.
The force of mortality is the exact steepness of that curve at the precise moment a person hits, say, 45 years, 3 months, 2 days, and 4 seconds old.
Wow.
It is the intensity of the mortality risk at that microscopic instant of time, assuming the person has survived up to that very moment.
Our sources referred to this as the speedometer of human aging.
I love that phrase.
It is a profoundly intimate way to look at the math. You are measuring the exact, instantaneous risk of a human life extinguishing at any frozen millisecond.
It is profound. And it
Yeah.
has massive practical implications for your exams and your career.
Like the Gompertz-Makeham law of mortality.
Exactly. You will undoubtedly encounter that in your studies. It's a mathematical model that perfectly illustrates this continuous rate of change.
Break that down for us.
It states that the force of mortality is made of 2 parts. First, a baseline constant.
Okay, what does the constant represent?
It represents accidental death, things that don't really depend on age, like getting struck by lightning.
Right, the risk of a car crash stays relatively flat whether you were 30 or 60.
Precisely. But then you add an exponential component to that constant.
And that represents the biological deterioration of aging.
Yes. The risk of death from heart disease curves upwards exponentially as the years tick by.
So to calibrate that exponential curve to match reality, actuaries actually take the derivative of real-world population data.
They do. They analyze the rate of change of mortality to pinpoint the exact parameters for that Gompertz-Makeham model.
And once they have that continuous function, they can integrate it to price a policy not just for a 45-year-old, but for a 45-year-old paying premiums monthly or even daily.
The continuous math, driven entirely by differentiation, allows for infinite precision in pricing.
Okay, so we use the force of mortality to figure out exactly when our policyholders might pass away, and we price their premiums accordingly.
That is step 1.
But that is only half the battle for an actuary.
Right, because you have to actually make sure the insurance company has the liquid cash to pay out those policies in 30 or 40 years.
Which means you are taking billions of dollars in premium payments and investing them heavily into the bond market.
And that brings us right back to the scenario we opened the deep dive with.
The microscopic shift in interest rates that threatens to wipe out a fund.
Exactly.
How does differentiation shield a multi-billion-dollar portfolio from an interest rate shock? Let's move into our second application, financial mathematics, specifically duration and convexity.
This is where we move from the biology of human life to the pure mechanics of financial markets.
Okay.
The relationship between the price of a bond and the interest rate in the market is inverse.
So if interest rates go up, the value of the bonds you already hold goes down.
They are on a seesaw.
Right. And because an insurance company or a pension fund holds massive liabilities payouts they absolutely must make in the future, they have to ensure that the value of their assets doesn't suddenly plummet and leave them insolvent.
They need to measure their exact sensitivity to interest rate movements.
So we use the first derivative. We calculate the slope.
Yes.
In finance, we call that first derivative duration.
Exactly.
The duration tells me if the central bank raises interest rates by 1% today, my bond portfolio will drop by exactly this percentage.
Yes, duration gives you the linear approximation. If you were to draw a graph with interest rates on the horizontal axis and bond prices on the vertical axis, the relationship is a downward sloping curve.
Okay, I am picturing the curve.
Duration is the act of drawing a straight tangent line against that curve at today's current interest rate.
Okay, I get duration, it's the immediate drop. But frankly, the next concept, convexity, kind of bends my brain a bit.
It trips up a lot of students.
If I already know my bond price is dropping because of duration, why do I care about convexity? Which is the second derivative, right?
It is.
If a massive shock hits, the money is already gone, isn't it? Why do I care about the acceleration of that drop?
That is a brilliant question, and it cuts to the heart of why linear approximations fail in the real world. Let's go back to that graph in your head.
Okay.
You drew a straight tangent line against a curve. At the exact point where they touch today's interest rate, the straight line and the curve are identical.
Right, they intersect perfectly.
But what happens if interest rates move drastically? Say, a massive 200 basis point jump.
Well, if I move far away from that starting point,
Yeah.
my straight tangent line is going to diverge entirely from the actual curve of the bond price.
Exactly. The straight line, your duration will predict that your bond price falls right off a cliff. It overestimates the loss.
Why does it overestimate?
Because the actual price-yield relationship of a standard bond is convex. It bows outward.
Oh, I see.
As interest rates get higher, the rate at which the bond price falls actually starts to slow down. The slope itself is flattening out.
The rate of
On the
change.
second derivative,
All right. Okay.
duration assumes the slope stays perfectly constant. Convexity measures how the slope itself bends.
So if you rely only on duration for a massive market shock, your mathematical model will be wildly inaccurate.
You will think you are bankrupt when you aren't. Or, worse, you'll think you are safe when you are massively overexposed.
This sounds exactly like a Taylor series expansion from calculus.
That is exactly what it is.
Yeah.
In a Taylor series, you approximate a complex function by adding up its derivatives.
Right.
The first-order term is the first derivative, which is duration. But to reduce the error of that straight line, you have to add the second-order term, the second derivative.
And that is convexity.
Yes. By adding convexity, you aren't just drawing a straight line against the curve, you are wrapping a parabola around it, matching its bend perfectly.
So how does an actuary actually use this as a shield? You mentioned the term immunization earlier.
Immunization is the holy grail of asset liability management.
Okay, how does it work?
An actuary will calculate the duration and the convexity of all the future payouts they owe their liabilities.
Got it.
Then they will construct a portfolio of bonds, their assets, that have the exact same duration and the exact same convexity.
Meaning if a massive, unprecedented interest rate shock hits the global market, both the assets and the liabilities will move in perfect lockstep.
Exactly. The curve of the assets perfectly hugs the curve of the liabilities.
They neutralize the shock wave.
Precisely. The surplus of the pension fund remains entirely insulated, whether rates go way up or way down.
But that perfect shield is entirely reliant on calculating the first and second derivatives accurately.
Without differentiation, the shield shatters.
That is incredible. The math doesn't just describe the market, it literally creates the armor against it.
It does.
But there is a glaring operational assumption we are making here, isn't there?
What's that?
To build these continuous Gompertz-Makeham survival models and to perfectly calculate the convexity of a massive portfolio, you need numbers.
Oh, yes.
You need parameters.
Right. You need to know the exact mean and variance of the claims you expect to hit your desk next year. You have to extract the actual truth from raw, messy data. How does an actuary find those perfect numbers?
They do it through predictive modeling and statistics. And the cornerstone technique for finding those perfect parameters is the maximum likelihood estimator, or MLE.
MLEs. They're ubiquitous in actuarial exams. If you are taking the statistics papers, you are dreaming about MLEs.
You definitely are.
Our source text used a fantastic metaphor for this that I want to explore.
The pitch black mountain.
Yes. Imagine you are dropped onto the side of a massive mountain, but it is pitch black dark.
Complete absolute darkness. You cannot see your hand in front of your face.
And your mission is to find the absolute highest peak of that mountain. You don't have a map and you don't have a flashlight. How do you find the summit?
Well, you have to use your feet.
Right. You use your feet to feel the slope of the ground immediately beneath you. And mathematically, that is differentiation.
You calculate the derivative at the exact coordinates where you are standing.
Yes. If your foot feels that the ground is slipping upward in front of you, meaning the instantaneous rate of change is positive, you need to take a step in that direction.
You take a step and you calculate the derivative again. Is the slope still positive? Keep walking.
You repeat this iterative, continuous process of feeling the slope. And eventually, you will take a step where the ground beneath your boots feels perfectly flat.
The steepness is completely gone.
At that exact moment, the rate of change, the derivative, is exactly zero.
And assuming the ground drops off in every direction around you, you know with absolute certainty that you are standing at the exact peak of the mountain.
Even in pitch black darkness.
I love that metaphor so much. But let's pivot and strip away the mountain. Let's look at the literal mathematical reality an actuary faces. In real life, that mountain is a probability function, right?
Specifically, it is the log likelihood function.
Okay, walk us through an example.
Let's say you have an auto insurance portfolio with 10,000 policyholders, and over the year, 500 of them file an auto claim.
Okay, raw data.
You believe the frequency of these claims follows a Poisson distribution.
Which is driven by a single parameter, lambda.
Yes. Lambda is the true underlying rate of claims. But you don't know what lambda is. You only have your raw data. 500 claims out of 10,000 people.
So the goal of the MLE is to find the specific value of lambda that makes our observed data, the 500, claims the absolute most probable outcome.
We want to find the peak of probability.
Exactly.
So you construct a likelihood function, which is the mathematical probability of observing your exact data given a theoretical lambda.
Now, computationally, likelihood functions involve multiplying thousands of probabilities together, right?
Yes, which is incredibly messy and leads to numbers so small that computers basically can't handle them.
Which is exactly why we take the natural logarithm of the likelihood function.
Logarithms possess this magical property of turning massive chains of multiplication into simple addition.
It makes the math incredibly elegant.
It does. So now you have your log likelihood function. That is your mountain.
Got it.
The horizontal axis is every possible value of lambda, and the vertical axis is the likelihood of your data.
So to find the peak, you do exactly what you did on the mountain. You take the first derivative of the log likelihood function with respect to the parameter lambda.
And in statistics, this first derivative is actually called the score function.
And just like standing on the flat peak, you set that derivative, that score function, exactly equal to 0.
You set it to 0, and you solve for lambda using algebra.
Wow.
The value of lambda that pops out of that equation is your maximum likelihood estimate. It is the absolute optimal parameter for your pricing model.
Extracted directly from the raw data using the logic of differentiation.
Exactly.
And again, the second derivative shows up to crash the party.
It always does.
Because finding the peak is great. But as an actuary, you also want to know how confident you should be in that estimate.
Right. Was it a sharp, distinct peak, like the Matterhorn, or was the mountain really wide and flat, meaning you could be standing anywhere near the top and still be relatively flat?
You are talking about the Fisher information matrix now.
I am, and you are spot on. The second derivative of the log likelihood function tells you the curvature of the peak.
Okay, so what if the second derivative is a massive negative number?
If it's a massive negative number, it means the slope is changing violently. The peak is incredibly sharp.
Meaning your estimate is highly precise, you have very little variance.
Conversely, if the second derivative is close to 0, the mountain is a flat plateau.
So your estimate has high variance, you have far less certainty about your parameter.
Exactly. The second derivative directly provides the standard error of your estimate.
It is just so satisfying how interconnected these concepts are. The exact same mathematical logic that tells you the acceleration of a bond's price drop is telling you the statistical variance of your auto insurance claims.
It's the universal language of sensitivity.
Okay, we have covered the continuous modeling of human mortality. We have covered shielding bonds with Taylor series approximations. We have covered climbing statistical mountains using log likelihoods.
We have covered a lot of ground.
Let's tackle the final frontier for today. This is an area of quantitative finance that is so intrinsically tied to calculus, the financial instruments themselves are literally named after the math.
Application number 4, financial economics and option pricing.
We are entering the realm of complex derivatives. Options, futures, swaps.
These are instruments whose value is derived from an underlying asset, like a stock or a commodity.
And because their value is tied to something else that is constantly moving, managing a portfolio of these instruments is basically an exercise in extreme real-time sensitivity analysis.
It absolutely is. And actuaries and quantitative traders measure this sensitivity using a suite of metrics universally known as the Greeks.
Delta, gamma, theta, vega.
Right. Let's unpack the most fundamental of the Greeks. Let's talk about delta.
Delta is, in its absolute purest form, a first derivative.
Yes. Let's say you own a call option on a tech stock. A call option gives you the right to buy that stock at a certain price in the future.
Okay.
If the price of the tech stock moves, the value of your option moves. Delta is simply the partial derivative of the option's price with respect to the underlying stock's price.
It's the immediate slope again.
Yes.
If the tech stock takes one microscopic step forward, say, it goes up by exactly 1 cent. Delta tells you exactly how many fractions of a cent the value of your option will change.
If we connect this to the broader Black-Scholes framework, delta is the ultimate instantaneous measure of exact exposure to the market.
So if you are an actuary, hedging a massive portfolio of variable annuities which often contain embedded options, you need to know your delta at all times.
You do. It brings all of Newton and Leibniz's abstract genius directly into a modern trading terminal.
But just knowing your delta isn't enough,
Yeah.
is it? Because we just established that the world is in perpetual motion.
It never stops.
Let's say I am a trader and I sell a $1 million call option to a client. I am suddenly exposed to massive risk.
Right. If the stock price moons, you owe the client a fortune.
So I need to hedge my position. I need to buy some of the underlying stock to cover my tracks. How much stock do I buy?
You look at your delta. If the delta of your option position is zero point 0.5, it means your option moves 50 cents for every dollar the stock moves.
Okay.
To create a perfectly neutral, shielded portfolio called a delta neutral hedge, you buy 50 shares of the underlying stock for every 100 options you sold.
The sensitivities perfectly cancel each other out.
Brilliant. You are perfectly shielded.
But here's the problem. 5 minutes later, the market opens and the tech stock jumps up by $2. My delta is no longer zero point 0.5. The slope has changed.
Exactly. Because the relationship between the option price and the stock price is a curve, not a straight line. Sound familiar?
It's the bond duration problem all over again.
It is the exact same mathematical phenomenon. As the stock price moves, the delta itself changes. Your hedge is suddenly broken.
You are exposed again.
And the rate at which your delta changes is measured by the second derivative of the option price.
In the options world, we don't call it convexity, though.
No, we call it gamma.
Gamma is the rate of change of the rate of change.
Yes. Gamma tells you how wildly your delta is going to swing when the market moves.
So if I have a high gamma,
If you have a high gamma, it means your delta is highly sensitive. Your hedge is incredibly fragile.
oh wow.
You will have to constantly frantically buy and sell the underlying stock every few minutes just to stay delta neutral.
This is called dynamic hedging, right?
Yes, and it generates massive transaction costs.
This just blows my mind. We started this conversation talking about Isaac Newton sitting on a farm in the 1660s, watching an apple fall from a branch, trying to figure out how to calculate its speed at a frozen instant. And centuries later, that exact same logic, the first and second derivatives, is hard-coded into trading algorithms on Wall Street, dictating the frantic buying and selling of millions of shares of stock a second just to manage the gamma of an options portfolio.
It is a profound legacy. And it brings us full circle to the very premise of today's deep dive.
Yeah.
Differentiation is not just a rote mechanical exercise of bringing the exponent down and subtracting one on a math test.
No, it is a lens.
Yeah.
It is the language of continuous reality. What an incredible journey we have taken today. We started by diagnosing the massive blind spot of the 1600s, a world standing still, trapped in snapshots.
We watched Newton and Leibniz shatter that paradigm, uncovering the mathematics of continuous flow.
We used the speedometer to grasp the philosophy of shrinking time to an infinitely small instant.
And most importantly for you, the actuarial student, we unpacked exactly how that exact philosophy governs everything you do.
Right. Taking the log of the survival function to find the instantaneous force of mortality.
Adding the second-order Taylor term of convexity to immunize a bond portfolio.
Setting the score function to 0 to conquer the pitch-black mountain of maximum likelihood estimator.
And constantly recalibrating delta and gamma to survive the chaotic volatility of the options market.
And if I can ask you to offer a final synthesis for the students listening.
Of course, when you are exhausted, when you are staring at a massive, convoluted calculus problem on an exam paper late at night, try to remember what you are actually doing.
You are not just pushing symbols around.
No, you are bringing a frozen, static view of the world to life. You are wielding the tool that empowers your entire profession to measure speed, to gauge complex sensitivities, and fundamentally to anticipate and manage the financial impacts of tomorrow, today.
It is a remarkable capability.
It really is.
That is the perfect way to frame it. But before we sign off, I want to leave you, the listener, with one final, slightly provocative thought to mull over. Something that builds on everything we've explored today.
Oh, I like where this is going.
We spent a lot of time talking about the second derivative convexity, gamma, the Fisher information matrix, measuring how fast the slope itself is changing, the acceleration.
Right.
But mathematics, as a pure abstract language, does not stop at 2.
No, it doesn't.
There is a third derivative. There's a fourth derivative, a fifth. In the world of physics, the third derivative of position, the rate of change of acceleration, is literally called jerk.
And the fourth is called snap.
Exactly. But think about this strictly in an actuarial or financial context. If you are already measuring the rate of change, and the rate of change, how deep down the rabbit hole of sensitivity can we practically go?
That is a fascinating question.
We know quantitative hedge funds look at the third derivative of option prices. They call it speed or color.
Yeah, they do.
But at what point does a fourth or fifth derivative become so microscopic, so fundamentally detached from the macro movements of human behavior and global markets, that the math becomes entirely disconnected from reality.
Are we finding deeper truths, or are we just obsessing over the mathematical noise?
Exactly. Does the universe just keep infinitely folding in on itself? Something to think about the next time you take a derivative. Good luck on those exams. Keep climbing those probability mountains in the dark and keep digging deeper into the numbers. We will see you next time.